Session management is the mechanism we use when building applications to track and maintain user state across multiple requests. There's lots of ways we can do this mechanically, but it's often storing unique session tokens in user storage or as cookies. When a user logs in, the server creates a session. The data attributed to it typically includes session tokens, user information, expiration details, and more. Session management is on what we refer to as the system's critical path. If it's down, pretty much nothing else works, so it's important to get it right and keep it performant. Now, your sessions have to live somewhere, and because it's often needed, sometimes with every single request, you would use an in-memory data store like Dragonfly when thinking about performance, possibly being able to avoid disk storage lookup at all. Now, let me take a moment to explain what Dragonfly is. It's a modern, high-performance in-memory data store that serves as a Redis alternative, but with a key difference. It's built with a multi-threaded architecture from the ground up. And this makes it particularly powerful for use cases like caching and session management in web applications. Now, what makes Dragonfly particularly effective for session management is that ability to handle millions of operations per second with sub-millisecond latency. This means that session management won't be a bottleneck to your applications, which is critical at scale. Plus, with Dragonfly's built-in persistence mechanisms, you automatically have the best trade-off between real-time backups and performance needs. Now let's take a look at how sessions actually work with Dragonfly by walking through a practical implementation in Go. First, we import the Redis client. As Dragonfly is fully compatible with the Redis wire protocol and commands, this should look familiar, and there's nothing Dragonfly specific here. We call it Dragonfly just so we know that it will be talking to a Dragonfly server and issuing commands to manipulate and retrieve data there. Then we initialize our client, pointing to our Dragonfly instance running locally at port 6380. Ultimately, our goal is to generate both an access token and a refresh token, and then store the refresh tokens in Dragonfly in the set data type using the sadd command. The set contains multiple refresh tokens, representing the multiple sessions of a user, maybe on different devices, for example. Here is a generate tokens function to be called when a user logs in. We generate a new access token using a function that we write elsewhere, and a new refresh token. And then we return both tokens in the response. We will create a key in the format that we want to store in Dragonfly and start a pipeline operation using Dragonfly, which allows us to issue multiple commands to reduce network round trips. We use the sadd command to add a new refresh token to the set in Dragonfly, and we also create a member level expiration on this new token using the field expire command, so that individual refresh tokens of this user can expire independently. Now, this is a Dragonfly specific feature. In Redis, at the time of recording, you can only expire the whole set instead of individual members in the set. Now we're setting this based on a configuration stored elsewhere, 7 days for example. So the refresh tokens will expire after 7 days. Now just as an aside, pipelining doesn't guarantee atomicity, which basically ensures that either all database operations occur or none occur. If you need a stronger guarantee of this, use a transaction, but that's not what we're using here for this example. The basic premise of extending a section is accepting a refresh token, generating a new access and refresh token pair, and returning both to the client. But first, we must validate that the provided value actually exists within the user's set of refresh tokens. Otherwise, it's invalid or the session has already expired. We create a key from the provided refresh token in the same format we used to store them, and then we use the sIsMember command to check if the provided value is a member of the set. Just like when we initially created the session, we start a pipeline, add the new value to the set, and set the token expiration. But this time, we'll pipe a third command in to remove the old refresh token from the set, as it has now been used and cannot be used again. Finally, logging out and destroying a session. This function removes the refresh token from Dragonfly using the srem command that we used in the last example. When logging out, the client should send a request to the server and then delete both tokens locally. This is just one example of how to use an in-memory data store for increased performance and scalability, allowing you to reduce bottlenecks in session retrieval, especially under heavy loads. As mentioned before, you can find the full project on GitHub, which contains all of the snippets we showed in this video. If you want to learn more, head to dragonflydb.io, where you can find various resources and the link to this project on GitHub. Thank you so much for joining me, and we'll see you in a future video.